Good afternoon, all. Professor Saketh will be continuing his talk on parameterized algorithms. Now he will discuss on parameterized streaming algorithms. Over to you, Professor.
Thanks a lot, Varsha. Okay, so yeah, eventually we will get to see streaming algorithms for sure. Yeah, but we'll continue our discussion from yesterday. And like as I told you, right, like to even introduce this new concepts, we need to introduce some of the techniques which has been largely used in these areas. So that has been my goal, to not only touch upon these new topics, but also on the way touch upon the other tools which probably could have been covered or should be covered in any small PC course. Okay. So just to go back, so what we did yesterday was like we tried to define the notion of like we talked about basic vertex cover algorithm. Then we talked about subset sum and how that can be viewed as a FPT algorithm with parameter log W, exponential in log W. Then we talked about what would it mean to have a factor 2 approximation in FPT time for vertex cover. And then we looked at what it means. We tried to understand some of these things. And then we saw two basics algorithms for approximation for vertex cover, one running in polynomial time, which was basically like you look at the matching edges, maximal matching edges, and pick both endpoints. And we saw how we can combine that with best known algorithm for vertex cover and do better. So first we looked at 1.5 approximation for vertex cover. And then we saw that there was nothing amazing about 1.5, depending on whether we wanted to get like there's some trade-off between running time and the quality of approximation algorithm that we could achieve. And we saw that at least for some points we saw. And as I told you, I mean, you can actually work out a formula based on given an alpha, what would be the running time. So for example, so if I was looking for a factor alpha approximation, okay. So for example, if I was looking for a factor alpha approximation, and I have say beta to the power k is the best known algorithm for a vertex cover, what would be the best beta sum alpha prime k, right? So you can compute this running time in terms of that, and that's an interesting size in its own. And then we decided to look that, okay, fine. I mean, the problem which is already FPT, it is interesting, but it may not be that interesting for a lot of people that why are you doing FPT approximation? Okay, but nevertheless, people do. And I will point you out to some other things also in a minute. And so then we looked at what would it mean to say problems does not belong to the class FPT. And I remember someone, a few mentioned that, look, graph coloring shouldn't be admit an FPT algorithm parameterized by the number of colors. And we saw why, because that would imply P equal to NP. And then we looked at what it means. Then we looked at graph coloring on planar graphs, and we saw that it has simply a simple 4/3 approximation algorithm for coloring. And then we thought, can we use this 4/3 approximation to design an approximation algorithm for graph coloring on almost planar graph? And by what is almost planar graph? A planar graph, like, I mean, a graph is called almost planar graph or apex graph if you can delete some k vertices to get a planar graph. And then we, in C power k or k power k running time, we gave 7/3 approximation, if I recall correctly. Yeah. So this is an approximation. We had 7/3 approximation yesterday. And then we went on to the area of what W hardness would mean. And we said or the hardness in FPT will mean, which is slightly independent from P versus NP. And then we started to make a class around click. Okay. And we saw that, okay, if the click is hard, then independent set is hard. But we saw that why such a reduction cannot happen for vertex cover, because the complexity of one is something and the complexity of other is something. And that is largely because we do not hope to have, like, you need to have some sort of parameter preservation during the reduction. And that is how we defined some things. And then we started to look at what was this problem, which was called partial vertex cover problem, where you're given a graph G, two numbers K and T, and you're looking for, you want to know whether you can cover at least T edges with at most K vertices, right? And we saw that if T is whole of the edges, this is the classical vertex cover problem. And then we try to show that, well, give a reduction for partial vertex cover, which would say that the partial vertex cover parameterized with the solution size k does not admit an FPT algorithm. So what would be that? So it would be like, so we gave a reduction from independent set, and basically for every vertex we added n minus degree v pendant vertices, and that's it. And then I hand waved my way out and say, hey, this is a valid reduction, which would mean that partial vertex cover does not have an FPT algorithm. Okay, so that is the starting point of our lecture today. So if you, unless you have some question here, I will move forward. Please let me know if you would like to ask me anything at this point of time. Okay, if not anything else, then let's start our today's lecture. Not talk, but lecture. Okay, so the theorem which we proved that the partial vertex cover parameterized by k does not have f of k n to the power big of 1 time algorithm unless click has one. Right? This is what here f is an arbitrary function depending on k alone. Okay, so this is what we showed. So this is our theorem we managed to show. If you trust me, is that this is what it is. Okay, okay, that partial vertex cover parameterized by k does not admit an FPT approximation. Does not admit an FPT algorithm. Okay, what about FPT approximation for this? Okay, so what I would like to do, okay, input is g and k, okay, okay, g, k, and t, and the parameter is, so like suppose what it mean by alpha factor f, parameter is going to be k, the running time measure, and the question will be either say that no k vertices can cover at least t edges. This you can return me an answer, then this is a no instant. Or find me k vertices that covers at least alpha time t number of edges. Right? This is what it means. Where some alpha is some less than equal to 1, some constant. Right? In fact, this has to be alpha has to be strictly less than 1, because alpha equal to 1 we can't hope to have such an algorithm, because in FPT time, because yeah, we got the problem is hard. Okay, so this is what I mean by alpha. So I don't change the budget. Only thing which I'm allowed to change is how many edges I'm able to cover. So rather than covering all the edges, all the t edges, my requirement, I'm allowed to cover some, say, half of the edges. Okay, for example. And we would like to make an algorithm for this problem as good as we can. Okay, and I will quantify that soon. But if I ask you, how will you go about designing an FPT approximation for this? What would be the natural, say, heuristics or natural heuristics to solve this problem? Do you understand the question? What would be the good heuristic to solve this problem? If you were a coder, so which vertex will you pick? Which vertex will you definitely pick first? If you would like to cover as many edges as possible, what would be the good heuristic? Like, what would be the good, not reduction? Yeah, I think heuristic is the right word for it.
A vertex with maximum degree, maybe.
Yes, correct. Greedy, as Pradisa is also greedy. Yes, that's it. So what will be the best thing to do? Okay, the best thing will be to do as follows. Okay, so here's my algorithm. Not algorithm, like here's my heuristic. Let's call greedy heuristic. What is my greedy heuristic? I arrange V1, V2, dot, Vn with the following property. Degree of V1 is at least degree of V2 and at least degree of Vn. So the vertices are arranged in decreasing order. Right? Do you agree? Right? And now maybe let's take S as first k vertices. Okay? V1, V2, Vk. Do you agree? This is one of the good heuristic. Like you take top k vertices of highest degree. Okay? Do you understand? Like, let's say, it just happens that suppose graph induced on S is an independent set. It just so happens. Can you say anything then? Then can you infer? If by luck, I looked at the V1 to Vk, highest degree vertices, top degree, and it just happened to be an independent set. Can I infer anything from this? Anybody? Right? Okay. And I know that all the edges are like this. It could be like this. It could be like this, like this, like this. But we do not have any edges here. Okay. Then my claim is, if S can cover at least T edges, then good. Else, it is a no instance. Meaning, no S vertices can cover more than this. Like, no other set can cover more edges than this set S can cover. Do you understand that? Like, if you understand this point, please put 1, if otherwise put 0. Right? So I'm saying very simple thing. Why? Because look, like when I get some other guy, it can only cover less than this. So it's a great case to be in. So the reason why this is not good, and this also should tell you why the problem is hard, because it is trying to like, it is like a set which is like an independent set and of high degree are actually a solution. But the problem is that S may not be independent. Correct. Great. But then I ask myself, fine, it is not an independent set, but how many edges can there be? In graph induced on S? Let's ask ourselves this. Anybody?
At most, cardinality of S choose 2.
Yes, so that is like K choose 2. Okay. So that's great, right? Now, let's ask ourselves, I say, hey, look at the top vertex, okay? Vertex V1. Okay, I'll ask, look at this is the top vertex. Suppose its degree is like, what can I say? What can I say then? Then notice that like, then this set is still will be a good approximation, because compared to what you are going to get from here and what you are going to lose, it means, look, why is the top vertex not an answer? Because look, the t must be much more than k to the power k power this, right? Because that is why single vertex is not a solution. So number of edges that I need to cover is much larger, but the amount I can lose here is only k choose 2, right? So even if I take all these guys, I'm only losing much less compared to I'm like a solution who would require it. Okay, so this is an intuition which we would like to make, which I would like to make explicit in my next approximation algorithm. Okay, so how do I say? I said, fine, here it is. I fix a number. My number is, this is like a, you will see, I fix a number which is d equal to k choose 2 divided by some epsilon. Okay, suppose this. Okay, now let's see what happens in case first. I say degree of V1 is greater than or equal to t. So the first vertex is really much like, I mean, it is like, it has degree proportional to, and epsilon is something which you have fixed, right? I will tell you, you will get what epsilon will be. Okay. Now I would like to know if in this case, if I pick the top k vertices, how good or what good quality solution I'm able to get. Is it really already a good approximation to the t? Like meaning that this set is really covering more or less as many edge a best set could cover. Let's try to ask ourselves. Okay. The reason why this set is not good compared to other, because it's not an independent set. So what happens that when you take a degree of some vertex, this edge is counted twice, one for u, other for v. So that is why, like, I mean, if you sum the degree of these guys, the only thing why it is not a good solution, because the double counting has meant that you are far off from optimum by at most k choose 2. But notice that no solution, no set S can cover more than summation degree of V. No set can cover more than these many edges. This is impossible, right? I'm not I'm saying that this set S doesn't cover. It may not cover all because there are lots of particularities. But forget about this. If I just count the degree, it means there are some edges which are double counted. Then in this case, whatever the bound we get, that is an upper bound that any set of size k can cover. Okay, so now I would like to exploit that in designing my algorithm. Okay, so how do you define an algorithm? So the algorithm's approximation algorithm, what is the size of the solution I'm returning divided by optimum? Okay, so what is the size of the solution I'm returning? I'm at least returning summation of dvi I equal to 1 to k minus k choose 2. Do you agree? Is it fine? Look, I'm definitely returning a solution whose value is summation degree of vi minus k choose 2. At least that many edges are definitely covered, because this covers those set of edges twice. And how many edges are you covering twice? Like in degree sum, at most k choose 2. So this is fine. Okay, so this much edges are made, and total number of edges that you can cover is upper bounded by summation I equal to 1 to k degree of vi, okay, which means that this is nothing but 1 minus k choose 2 divided by summation I equal to 1 to k dvi. So now I ask myself, which case I am? Oh, degree of V1 is greater than or equal to D, which implies degree of V1 is greater than or equal to D, okay? Which is what? D is at least K choose 2, or this is equal to epsilon, right? Now, so from here, I would like to say, so K choose 2 is equal to epsilon times D. So let's substitute this here. Okay, now what can I say about summation I equal to 1 to k dvi? I claim that this number is definitely more than D, because what is D? Look, degree of V1 is at least D. So this others can only contribute more to the left side compared to the right side, which implies this is greater than or equal to 1 minus epsilon D to the power D, which implies that this is 1 minus epsilon. So what are we able to show? We are able to show that the solution we are going to return, solution, is at least 1 minus epsilon times opt. So in fact, epsilon, any small constant you choose, okay, we are able to show that if I'll take the top k vertices, then in this case, this already provides a 1 minus epsilon approximation to my partial vertex cover problem. Is this okay to you? Or if you want me to make you understand this inequality, then I can help you with that too. Okay. So these inequalities are not amazingly hard, because what is happening here? It is 1 minus k choose 2 divided by something. So if you replace this with something smaller, then or something, sorry, bigger. Yeah. So it's much larger quantity you are removing. So sorry, if you put it by something smaller, then larger, then what is it? Then this is a bigger number, and then you are subtracting something more. So this is lower bound happens. And similarly, you can work out with these things, and right, yeah, and you can make it work. Okay. So this is basically, we can get 1 minus epsilon. How much time did this algorithm took? How much time? How much time this step took? Can anybody tell me? What did the algorithm do? It looked at the vertices, it sorted them by their degrees. Okay, it checked whether the first degree, or like top degree, is at least D or not. If it is at least D, then it said, okay, fine, take the top k vertices, and that's your solution. That's all that did. How much time will this, whatever I just now told, will take? Yeah, fine. So basically polynomial time. That's all that I needed. Okay. So are we done, or there is still something more to be done? Why will this algorithm not work? In which case? When this case is not going to work, when the following happens. Okay. Degree of V1 is less than or equal to D, which is equal to k choose 2 divided by epsilon. If this happens, then it is not going to work. Am I right? Then can you tell me what can, if this is a case, in this case too, what is an upper bound on T? Like, what is a, like, what can I say that, look, if T is more than this, then say no. You can never cover with k vertices more than this many edges. Can you provide an upper bound? We know the degree of top vertex is bounded by k choose 2 epsilon. How much more edges can you, then if this is the case, it means the graph has maximum degree bounded by D. How many edges can you cover with k vertices? How many edges can you cover? Anybody? If a graph has maximum degree bounded by D, then K vertices can cover how many edges?
KD by 2.
Why KD by 2?
No, so, I mean, in the worst case, everybody can have a degree D.
Yeah, so they can cover
KD.
KD edges for sure. So I don't think there's 2 here. From where will I get 2?
Okay.
But my question is, can K vertices cover KD plus 53 edges? Is it possible? Hey, no, because if K vertices cover KD plus 53, then there is at least one vertex which covers at least D plus 53 by K. Not possible. Because which means imply that it covers D plus 1 edges, but maximum degree is upper bounded by D, right? So in this case, what happens is that T is at most KD, okay? So basically now our question has been reduced to the following, okay? Does there exist K vertices that covers KD edges, right? At least KD edges, okay? But now we will take a break here and we'll come back to this question in a while, okay? So what I mean by this, so you will see, we will take a break from this question and we will go back to our partial vertex cover question, okay? What was our partial vertex cover question? It was here. Copy. Paste. Okay. Yeah. So, okay. So now I'm going to design an algorithm for partial vertex cover, say parameterized by T, right? You saw that the problem is W1 hard or problem cannot have an FP algorithm parameterized by K. But what about T? Suppose if I can give you an algorithm with running time f of t times n to the power big of 1. Suppose I can give you such an algorithm. What does this algorithm imply for this case? Then it would imply that, okay, in this case, the number of edges that I'm allowed to cover is at most KD. So now if I apply that algorithm, okay, if I apply that algorithm, then my running time will be f of KD, right, times n to the power big of 1. So what will be f of KD? What is D? Is like some, say, K square by epsilon, something like that. So it's like it is going to be some FK cube and epsilon time n to the power big of. So it means we are able to get, in this case, we will exactly solve the problem. So what I'm saying, so what happens in this? So we have two cases. Either the degree is really much large compared to K choose 2 and epsilon, then return the top K guys, and then you are done. In the other case, I don't know how to handle, but I know that K vertices can only cover number of edges, which is function of K itself and epsilon. Then in that case, I will exactly solve the problem. Hence, I am done with the optimum. So in case 2, the factor of approximation is 1. In case 1, factor of approximation is 1 minus epsilon, right? So the approximation of them has like factor 1 minus epsilon, and the running time, which depends on K and epsilon. Okay, so we have designed, if I give, so we will be designing f of K minus epsilon approximation algorithm for partial vertex cover with factor 1 minus epsilon, right? So what we are able to do, we are able to give an FPT algorithm which has a property that it returns, you choose your favorite epsilon, then this algorithm will run in the K and the favorite epsilon that you chose, and it will return me an 1 minus epsilon approximation, meaning it will return me a k-size set that will cover at least 1 minus epsilon times t number of edges. Okay, so that is what will happen if I'm able to show problem is FPT parameterized by number of edges that I need to cover. Okay, is that fine? So please let me know if you have understood what will happen if I'm able to show this problem is FPT parameterized by t for FPT approximation. Okay, then please put +1. So do I assume that none of you people understood what happened? Okay, there are at least some people. Okay, so even if you did not understand what happened, let's treat this problem partial vertex cover as it is now. We would like to design an algorithm for partial vertex cover parameterized by t. So even if you did not understand what I said up until now, you can wake up and just focus on this. We'll come back to the FPT approximation once we have designed an FPT algorithm for this. So whatever we have said up until now will not be required to design an FPT algorithm for partial vertex cover parameterized by the number of edges. Is this fine? Is this okay? Okay. So here is my algorithm. My algorithm is a bit funky. Okay. So my algorithm is a bit randomized. So what is the step 1 of my algorithm? Color every edge of G uniformly at random from a color set 1 to T. So what is the meaning of this? I go to every edge. Okay. I go to every edge. Okay. I go to every edge. I toss a coin with T faces, and whichever number comes, I just put it this. Okay. Is the process clear? Now I want to know, okay, I did this. Very nice. Step 2. Let W be the set of edges that can be covered with k vertices, right? So basically what I mean to say that there's a set S which covers at least T edges, okay? This covers T edges, okay? W is the set of T edges incident to S. But suppose S covers like more than T edges, like just, I don't care. Then I delete some edges for that matter. Like, I mean, in W, I only keep some T edges incident to this set of S, but it could be that it is covering a lot, but I'm only going to be interested in that. Okay. Now I ask myself, what is the probability that edges in T have been colored with different colors, right? So set size is T, right? And I want to say, look, what is the probability that if I look at the edges in W, no color is repeated on edges of W? What is the probability of that? Okay, so suppose this is my good event. What is a good event? Edges of W are properly colored. Edges of W are colorful, right? No color is repeated, right? This is the meaning of this. So for example, here oh no. Okay, something went wrong. Crashed. Okay, fine. So what is my good event? My good event is that edges in W are properly are colorful. No two edges in W get the same color. Okay. Okay. So for example, suppose these are my edges. Let's color like a child. Okay. My son likes to enjoy this, so I like. So this is like a yellow color. This gets green color. This gets purple color. Okay. And this gets some orange color, right? Then these are my colorful edges. But suppose if I would have given this also some green, then this is not colorful. So I'm just asking you, what is the probability that the edges of W have become colorful? Anybody? Can anybody do this computation for me? Okay. So we are interested in what is the probability that good event happens, that is W is colorful. Come on. Suppose the graph has M edges. So here all possible colorings, and here good coloring. Agreed? Is this fine? How many possible colorings are there? So basically I'm asking how many functions are there from 1 to M to 1 to T. How many functions are there? Because all possible colorings means any edge can get any color.
T over.
Okay. Yeah. So any edge can get T colors. So they're T. Excellent. Okay. Okay. So this is T to the power M. And what is a good coloring? Okay. Good coloring is that, I mean, good coloring is that like here are like, suppose these are the edges of W, and suppose these are like other edges, I don't care what these edges get. Do you agree? I don't care, right? So for this, how many such edges are there? M minus T. I'm fine if they get any of the T colors. But what about these T edges of W? What should happen? Suppose this is my edge 1, 2, 3, ... T. How many choices do we have for color for edge 1? How many colors can I give? Which all colors are allowed? T. Okay, great. For 2?
T minus 1.
Correct. For 3?
T minus 2.
So on and so forth, right? So this is basically T factorial. Okay, agreed? So now, so the probability is good coloring divided by M power T. Excellent. So what is left? So this is equal to T factorial divided by T power T, right? And if you apply some known bounds, this is this, where what is E? E is base of natural log, and here I have used Stirling approximation. Okay. Do you agree? Right. Excellent. So probability of being good is like 1 over E power T, which is like just a function of T alone, which is great for us. Okay. Okay. So we will worry about this. So now let's look at the step 2 of our algorithm. Okay. What is step 2 of my algorithm? Step 2 is, okay, assume a coloring f from h set of g to 1 to t such that w is colorful. Okay. Question. Can we find w given this coloring? Right? So there's a good property of this coloring. What is the good property of this coloring? The good property of this coloring is that every edge in W is colored with different colors. Okay. Can I extract this property? Can we use this additional structure given by this coloring to get my solution? Okay. And this is what I'll tell you. Okay. So I said, fine, fine, fine. Okay, good. So look at, okay, I said, look, here's my some set S. Okay, here's my some set S, and there are some vertices. Okay, now let's guess. Oh, I don't know these vertices. This is my job to find. But I said, okay, the first vertex covers edges of color red, green, purple, orange. Excellent. Oh, so this is my first prescription. Okay. Second vertex, like this vertex, covers, say, edges of color. Okay, I only know few colors, say blue, brown, black, and so on. Right. So you guess. Right. Okay. So what I have guessed, these k vertices. Okay. So which all colored edges this vertex covers? Which all colored edges this vertex covered? Which all color? Okay. I guess this. Right. So this is an assignment h from 1 to k to 1 to t such that it partitions t. How many such partitions are there? How many such functions will be there? That it should partition my 1 to 2 t into k parts. Anybody? Right? It's very simple, right? In how many ways can you partition 1 to t into k parts? I mean, I want no repetition, but even if I like, yeah. For first vertex, you guess a subset, right? First vertex, you guess a subset of 1 to t, right? For the next vertex, what will you do? You guess the subset from the remaining guy. So suppose whatever it is, like some at most 2 power t, so on and so forth, right? So this is at most 2 to the power kt. I mean, this is bad. In fact, this is just k power t. You can prove that this is nothing but k power t because it's basically a function, right? So I think this is not the right way of writing it. I think the right way should be 1 to t to 1 to k. Okay. So yeah, now is it easy to see that this is nothing but k to the power t because first vertex has how many? Any part it can go. Second vertex, so it is like this is k power t, right? So it was my mistake of writing 1 to k. No, this is basically partition is given by nothing but a function from 1 to t to 1 to k such that every element is assigned. Okay. Is this fine? If this is fine, then please put +1. Okay. So I guess this also. Okay. So I guess this also partition. So suppose you have H from 1 to K to 1 to T. Okay. So I ask myself, okay, fine. Okay, 1 to K. I say, look at H inverse of 1. Which all colors are here? Which is same as, now you know, okay, so there is a vertex which has color red, green, purple, red. Can you now check, is there a vertex which has an edge incident which is red, green, purple, orange? Can I check this in polytime? Look, you have been given this colorful graph and I ask you the following question. Is there a vertex which has been assigned color red, green, purple, orange? Can I check this in polytime now? Yes, no, if you think we can do it, then put +1. Right? So what does this imply? Is that if you are given an H function, I can check if there exists V1, V2, Vk such that Vi covers edges of the Vi covers edges Vi covers edges in the set H inverse of I. That's it. And this I can check in polytime, right? I look at this vertex of this. Okay. If I succeed, what happens? What happens? Then actually we have found K vertices, right? That they are covering some edges, and number of edges that they are able to cover is at least the number of colorful edges, right? So these K vertices, if I'm able to find such K vertices, then they will cover at least T edges and I'm happy, right? So notice that how many choices of those functions are. So basically the second step of the algorithm will run in time K power T, okay, K power T, okay, and n to the power big O of 1. So if for any function, if I find these K vertices which covers these T edges, and how are we guaranteed that they will cover T edges? Because the way we have recorded the colors on these edges, then they are good. Okay. So now I ask myself, fine, but my whole algorithm was randomized algorithm. I first colored every edge of G with colors 1 to T. Okay, then with probability 1 over e power t, we have a property that the color of W has become colorful. If the colors have become W, then I can apply my step 2, which runs in time this. So notice this is a running time of the algorithm. And what is the success probability of this algorithm? Success probability is that, hey, S has the property that it has. And we know that this property holds with 1 over e power t time. Okay, so the running time of this algorithm is K power T n to the power big O of 1, but the success probability is 1 over e to the power t. It means, how can I do, what can I do to make the success probability constant? Do you know any trick to make a constant probability success? Success probability, can you boost this success probability to constant? Anybody?
Repeat this incident e to the power t times.
Yeah. So there's a suggestion. Repeat the whole process, the whole algorithm, e power t times. Okay, and if any one of the process, any of the what do you call, any of the round succeeds, you say success. Else, you say fail. So now let's see what happens to the success probability. Okay. So to do this, I'm going to say, what is the probability that algorithm succeeds is same as 1 minus probability that algorithm failed. Okay. So why will algorithm fail? Probability that algorithm fails is probability that algorithm fails in round 1 and round 2 and round t. Hey, but look, these algorithms are run independently. It means if I think of them as a random, like what is that called? Random variables, the success or the failure probability, then in each round, the random coins that I use are different, are independent. So because of the independence of these rounds, what I can say is nothing but this is probability I equal to 1 to t, probability that algorithm fails in round I. What is the probability that algorithm fails in round I? We know that it succeeds with probability 1 over e power t. So it fails with probability. So this is probability I equal to 1 to t, 1 minus 1 over e to the power. So not this is round e power t. Sorry, this is my mistake. Okay. And here it is e power t. Okay. Which implies that this is nothing but 1 minus 1 over e power t to the power e power t, which is upper bounded by 1 over e, right? Which implies that we will succeed with probability. How much? At least we will succeed with probability 1 minus 1 over e, which is like some constant, like at least greater than half. Okay. So actually, this is how randomized algorithm is done. So if a randomized algorithm has some failure probability, right? So it's like, imagine that, okay, if I ask you the following question. So like, suppose probability of getting a coin, getting a head is like, probability of getting a head is like 1/4. Then how many number of steps do I need to do so that I'm guaranteed to get at least one head with good probability? It's like expected number is like 4, like 1 over p. So similarly here. So if I succeeded with probability 1 over e power t, then to boost my success probability, I should run this experiment e power t times and then choose the best answer from there, right? So this is exactly what, this is nothing about this algorithm in particular. This is a strategy which is used in all the randomized algorithms to boost the success probability when by doing what is called independent runs or independent trials, whatever it is. Okay. So now we have boosted this algorithm. So the running time of the algorithm is, now if you notice, my running time of this algorithm is okay. So running time of this algorithm is e power t like times for the repetition, and in each round we had this k power t times n to the power big O of 1. Okay. So this is, and the success, this is a randomized algorithm with success probability some constant, say half. Look, we could have made this arbitrarily close to success probability by, for example, repeating this e power t log n times, then it will be e power log n. So success failure probability is upper bounded by 1 over n. The success probability is 1 minus 1 by n, which is great. I mean, if you have taken just some, not log n, not repeated this algorithm e power t times, but e power t log n time. What happens if I repeat this algorithm e power t times to the power n times? Then it will be 1 over e power n. So success probability is 1 minus 1 by e to the power n. So like you can really get close to 1 your success probability by repeating sufficiently many times. Okay. 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 But now you can ask me the question, why is k greater than or equal to, like, how will I say that this is like e power t, some t power t into the, because we were trying to make an algorithm with running time, which was solely dependent on f of t. So can I say that t is greater than or equal to k? Okay. This is a question for you to think. But for sure, this is an FPT algorithm parameterized by K plus T. Okay. But this is like very simple exercise. This is why I left. And for us, this is good enough, right? Because for FPT approximation, all we needed was to have an algorithm for the case when T is at most KD. Look at what happens here. Okay. Now for us, T is like at most K time D, which is like, say, less than equal to K cube over epsilon. Fine. So we are happy. So now our algorithm runs in time e power K cube over epsilon times K power Kq over epsilon n to the power big one. And then this and gives us, so this is an algorithm which runs in time, which running time depends on f k comma epsilon times n to the power big of 1. And so we are getting an FPT approximation in k comma epsilon. So look, for example, if you're looking for 1.5 approximation, then I substitute epsilon equal to 1.5, then this is approximation in just function of k alone, right? So, I mean, it's just that when you start to get closer and closer to 1, because the problem is W1 hard, I need to have some dependence on epsilon, okay? So that's the point. So this is good enough for me. Now, the method which I taught you, this is exactly what is called, if you open the book on the parameterized complexity, this is called color coding, okay? So the reason of teaching you this is that, in my opinion, FPT world is incomplete without color coding. So what was the method? So the method was very simple. I knew the number of objects, okay? And I wanted to find this number of these objects by doing colorfully maintaining something, okay? So for example, I could have applied the same philosophy for, say, longest path. What is the longest path problem? You are given a graph G and K, and you are asking, does there exist a path on K vertices? Okay, fine. So what will be my algorithm? My algorithm is very simple. I still will do color the vertex set with colors 1 to K. Okay. Good event, look at fix some path P on K vertices, say V1, V2, Vk. Good event, P is colored full. Okay. What is the size of P? If you do the same, this thing, you can say, oh, this is with probability 1 over e power K. Okay, it is colored full. Okay. So now, what I know, I have a function to me from vertex set of G to 1 to K such that P is colored full. Find P. Very easy. Find P. I say, haha, I need to find P. So like a child, I write down this. I say, hey, the first color is red. Second color is blue. Third color is green. Fourth color is orange. Fifth color is whatever. I mean, I don't know. Pink. I don't even know that. Fine. So now what I will do, I will make a directed. I will make a graph. I say, look at all the vertices which is going to come, which are red. I put them together like a partition. I say, hey, I know that if I'm looking for a path after red, which color comes? Blue comes. Fine. Then let's go to the blue. Let's put down all the vertices which are going to come blue, which are going to come green, so on and so forth. I know that the path which I'm looking for, first edge is red, blue edge. Then I don't need a red and blue. So you delete all edges which are going across. That's okay. So I deleted all the edges which are going across, like going from this to anybody else but the next consecutive layer. I know that I'm not going to use edges in the same color class, so I make them independent. Okay. So basically what I have this partitioned graph where edges are going just here, here, and here. Okay. So now what I do, I say, okay, fine. I put an S, make him adjacent to everybody here in the first, and make everything directed from left to right. and add this. Notice that if there's a directed path from S to T, then S must go to the first color class, then it go to the second color class, then it go to the third color class, so on and so forth. So if there is a path from S to T, it means you can get a path of length K in G. Okay. So what is the running time of this algorithm? Running time is like, first step is free because you're doing uniformly at random coloring the vertices. Second is that you are guessing this permutation of colors like red, blue, that is K factorial. And once you have guessed this is polynomial time because you make up this graph and you do ST connectivity. Fine. But the success probability is 1 over e power K. So you need to repeat this algorithm e power K times and do the same analysis and get e power K times K factorial n to the power big O of 1. Hey, done. In fact, what happens is that given this function, you can find this coloring using dynamic programming in 2 power K time. So actually this algorithm will give you 2e to the power K n to the power big O of 1. Right? And so basically color coding started from this particular algorithm. So there was a motivation to do this problem. Then in 1994, Alan Euster and Noga Euster and Heuristic found this method of color coding, which is a very classical method. It has found applications well beyond the boundary of parameterized algorithms. And what I taught you for partial vertex cover is an algorithm using this methodology in details. So my suggestion will be that if you enjoy some of these things, then go and have a look at these kind of algorithms. Okay, guys. So any questions on partial vertex cover? Partial vertex cover algorithm parameterized by K plus T, and an outline of an algorithm for longest path before we change our guard. We change and move to something completely different. Any question? If not, if you're happy with what happened, you can put +1. And even if you're switched off, you can switch on now because we will do entirely different thing, nothing of what we discussed up until now. Okay. Okay. A technique. The reason why I taught you technique of color coding is, first of all, it's fundamental, and all these aligning area of Fpt approximation, streaming, they use color coding fundamentally in many of their algorithms. So it's a good technique or tool to have in your armor. Okay. So now I'm going to change my guard, and I'm going to talk about graph streaming. Actually, I need to talk about parameterized graph streaming. Okay. Hopefully, I will be able to convince you that's an interesting area in next half an hour. So first, model. What's a model of computation here? Okay. So in this model, what happens is that edges are coming in a stream. Okay. Edges are coming in stream one at a time. Okay. And you have space here to store some sketch of graphs seen so far. So this is a sketch. And after the process and after all the edges are over, you need to decide some problem based on your sketch. Goal: use as small space as possible for as small as possible to solve your problem. Okay. Gold standard. Okay. Gold standard is, in this world, is log n to the power big O of 1 space. This is your gold standard. standard. Okay. Look, I'm not talking about solving or nothing. So edges are coming. Okay. Based on that, you like to store something so that at the end, I will ask, like, you know, for which problem you're solving this sketch or keeping this sketch. At the end, when the stream ends, you need to be able to answer questions or queries about the whole graph, looking at just your sketch. So, okay, so this is a gold standard. So the first problem which I want to talk to you about today is connectivity problem. Okay. So what do I want to do? So given a graph G, edges are coming in stream. After the stream ends, you like to answer queries of the form, is U and V connected in G? It need not be deterministic, but let's focus ourselves to be deterministic. Okay. Okay. For now, we'll worry about deterministic. Okay. So for now, edges are just coming. Okay. Edges are not deleted, nothing. Edges come, and they go. This is called insertion only model. Okay. Like we are only doing insertion, not deleting. Okay. Insertion only model. And we will focus only on this today. There is much more general model where edges can come and like some edges are deleted. At the end, whatever the graph you get by insertion and deletion, for that corresponding to that graph, your sketch should be able to answer. But we'll not worry about this. For now, only edges happen. And I want to do this connectivity. Okay. So edges are coming. What should you do? Can you suggest me what could be the good thing to keep so that I don't keep too many edges? Okay, what do you mean by this? So how much space will it take? Prashant, can you unmute yourself and tell others also about your idea? If you don't mind. You have a correct idea, so maybe you'd like to share with others and explain a bit.
Sir, I was just thinking about a data structure called a disjoint set. You basically keep adding sets, and if it's connected, you can quickly answer that. But I'm thinking about the space that will take, like, because we have like this log n to the power of 1, if I'm not wrong.
No. Don't worry about that. That's a gold standard. Okay.
Yeah.
We may not be able to achieve this. So forget about that you want to do it. I just want to know if you use this strategy, how much space will it take? Is that clear to you?
Yes, sir. So in that case, we would basically be storing the number of nodes. So
how much space should they take? Suppose nodes are numbered from 1 to n. How many bits do you need to store one vertex?
Log n.
Correct. So what is the total number of bits will be storing then?
N log n.
Correct. It's still better than n square, no? That is the number of edges we could have in the graph, right?
Yes, sir. Yeah.
Right. So compared to storing all the edges, which could be n square, we're definitely saving a lot, because while it's like there could be quadratic number of edges in the graph, but the amount of information that we're storing is just linear in n. Am I right? Like
yes,
roughly n log n, right? And now looking at this data structure or whatever you have done, what you have done now for every pair of, like when I give you a pair of vertex, you can quickly look up into this. Are they in the same connected component? If they are, you say yes, otherwise no. And it correctly, faithfully reflects the data structure that has gone by. Am I right?
Yes, sir. Yeah.
So just to put this into a human language, okay, for those who may not. So basically what we will do, we will maintain spanning forest. Okay, we are going to maintain spanning forest. Okay, what is the meaning of spanning forest? So at any point of time, we are keeping this spanning forest in my graph. Okay, new edge comes, I check. If new edge comes, what happens? If this edge is in the same, like if the edge makes puts a cycle in this forest, in the tree, what will I do? Should I keep this edge? No, because it is not giving me any information, no extra information, right? So if such an edge comes, you let it go, right? It's like I anyway have this information that these set of elements are connected. What more extra information is it providing me, right? But if this edge was going across, is it providing me extra information? Yes or no?
Yes.
Exactly. Because now you have got a bigger tree, because now you know more information. Not only these guys are connected among each other, even this. So basically, you are never going to keep more than n-1 edges. And to keep this n-1 edges in their connected component piece, it's like, this is exactly what is disjoint data structure is about, right? That this was disjoint. Now, when I add this edge, are this disjoint? No, merge them, right? So if I forget about disjoint data structure, I could maintain this spanning forest, and this will take n log n space. Okay. Okay, good. So is this clear? It was simple. And actually we can prove that you need big O of n log n space. Like you cannot do better, much better. Okay, this is like, let me put in quote. Okay. So in some sense, this simple algorithm is also the optimal algorithm for the problem of our consideration. Okay. So what happens is that this is a gold standard, but most graph problems cannot meet this gold standard. You can show a lower bound that you at least need omega in space, at least. So then what is the point? So people ask, but still, graph can have n square edges, but if you're able to do something in n polylog in edges, it's great for us. Is in Uber, what you write?
Yeah, you are saying that if I get an edge which is not giving me more information, you can drop it.
Yes.
I'm just trying to understand this physically in terms of in Uber situation, if a new origin destination pair comes in.
Okay.
So how do you conceptually keep that information? Do you say someone else has already asked for an origin destination of the same? If someone else asks, how does this?
No, like you shouldn't look. That's a very different scenario to apply.
Okay.
Right.
Okay.
Here, I had much very simple information. Like the very simple information was that, can I reach from here to here or not?
Okay.
Is this place reachable or not? Right. In a graph. Right. So if you think of a distance and locations, like maybe some place, some city and some city are connected, and some city and some city are not connected. But if you notice that, if I knew that some cities are connected among each other, and I told you that, in that these two cities are connected, that doesn't give me any extra information. I knew this information anyway. All you just now said that, between them, there's a direct path. I mean, direct road. I mean, sure, I don't care. If the only thing which I worried about is, can I go from here to here?
Okay.
That's it. Yeah. Thanks. Okay. So, people were, so what is defined in graph algorithm is something called semi-streaming. Okay, semi-streaming, where we say, our gold standard will be for graph problem is like, if I allow you n polylog of n space. Okay, so people fight for this, and there are several interesting problems for which you can get such an algorithm. It's an amazing area of research which is very flourishing and happening. It's a happening area, to be honest, because of lots of motivation from, as Iswaran was telling, from the practical life and practical motivation. So this is very, very well studied area and well studied problem. But before I end today's lecture, I was supposed to tell you about something about parameterized graph streaming. So let me make the algorithm which Pradisha taught you the first day for vertex cover in streaming setting. Okay, what I mean by this. Okay, so people define in parameterized world, okay, the following kind of classes. I said, okay, maybe polylogin is not good enough. Let's allow spaces which is like k power big O of O log big O of n. So this is considered gold standard in FPT setting, right? Because look, now I have parameterized space, right? So I would like to save, I want to solve say vertex cover problem, but edges are going by, and but I only can keep k power big O of O 1 log big O of 1 space. I will tell you this, give you this algorithm. But very soon we realize that this is also very restrictive. Okay, and very recently we have defined this notion. Now it was already defined in 2019 by Cormode and Chitnis, that actually there's something called semi-parameterized streaming, right? So as the name suggests, I'm going to allow you not only this k power big O of 1 n polylog n space. Okay, and we recently we wrote an article and where we showed that in fact, if you allow such kind of spaces, then many natural problems in parameterized algorithms can be run into this. Okay, but that's a topic of discussion for some other day. But today, what I want to do is the following as my end lecture, as my end example is the following I would like to do. Vertex cover. Okay, this you can think of the streaming kernel also. So input is G comma K. G not coming in the static setting, coming in streaming, insertion only model. And I will talk about non-insertion model at the end of this lecture. Okay, streaming, parameter is K. The question, the G has a vertex cover of size at most K. That's it. So what I will do, I'm going to keep a G prime subgraph of G, okay, with the following property. Number of edges in G prime is going to be roughly, say, I think k to the power big O of 1. I think it should be just k square, but we'll see how much it is. And the property will be that G prime has a vertex cover of size at most k if and only if G has a vertex cover of size at most k. So I'm going to give you a kernel for vertex cover in streaming setting, the way Pradisha gave you a kernel for vertex cover in static setting. Right? So I'm going to give you the same kernel which Pradisha gave you, but now I'm going to give you this kernel. Like I need to do more work because edges are coming, and I only have to make I have to make some judgment or some decision call then and there. I can't see the whole thing. Okay. Okay. So here's my algorithm. Very simple. Okay. E1, E2, EM coming. Okay. So I'm going to maintain an invariant. What is my invariant? Here. Okay. And 1. Maintain a maximal matching M. Okay. In the beginning, so this is what I will store. In the beginning, M is empty set. Okay. That's it. Okay. And what I would like to do is add some additional edges. I will call it degree edges. You will see what I mean. So basically, I'm going to keep for every vertex in vertex set of M in the matching edges, keep as many as k plus 2 edges if possible. Actually, I don't know what this number is. This is what I put. So we'll see how it happens. So in the beginning, M is empty. And suppose some edge comes. What is my first question? Can I add this to maximum matching, which I'm keeping? That's the first question. New edge comes. Question number 1. Can I add E to M? Easy to check, right? Right? I just check. When can I add it? If this edge does not meet with any of the endpoint, then I can add. Okay. Okay. Otherwise, no. Second question I ask myself. Do I need to keep E for degree purposes? Okay. So I ask. Fine. Okay. So I have M. I have, say, vertex set of M. I said, and I'm keeping this G prime also, which was empty in the beginning. So I said, okay, fine. What is the, is there a, okay, so what I will ask is the following question. So suppose E is UV. Is degree of U in G prime greater than or equal to K plus 2? I ask myself, yes or no. Two questions. I will tell you what I will. Okay. If it is yes, I move to the next question. Question number, if no, then I will say keep E to G prime. But if suppose it says yes, then I ask another question. What is degree of V in G prime at least K plus 2? It says yes, then I will tell. It says no, then I will say keep E to G prime. If it says yes, then I'll say forget E, right? So I have a very simple procedure. I'm maintaining a M and G prime. M is also part of G prime, by the way. Okay. So I say, do you increase my matching size? If it is, let me add you to M. Okay. If not, then I say, hey, will you help me getting the degree of U a lot? Like lot means greater or equal to K plus 2. Yes. Degree of U is much lower than K, like is strictly less than K plus 2. Then I say, okay, then just add in, because you have help in increasing the degree of U by 1. Say, no. U doesn't need any help. Its degree is already K plus 2. I said, fine. I don't care then. Okay, then I look at V. Okay, so what happens to V? Okay, V, I ask the same question. Hey, do you need me to help you get your degree to K plus 2? If it says, no, I don't. If it says, yeah, I need you to help, then I add this. Otherwise, none of them need it because their degrees are already more. Then what I do? I just let this edge go away. Okay, so this is my whole procedure. Fine. Okay, that's it. Okay. So I also need to add something more. So I should have a 0 step. Okay, can I add I to M? What can you say if cardinality of M becomes more than K? What can you say? Then you say, you can immediately, then don't store anything. Like just keep K plus 1 edges in M. After that, don't do anything at all. Why? Because now this K plus 1 matching edges will tell you anyway, G does not have a vertex 4 of size K because M is there. So you only need to keep this K plus 1 edges and forget everything. So let's assume that the M is at most K. Okay. M never grows more than K throughout the process. Now I have to show two things to you. First, G and G prime are equivalent, meaning if I can solve vertex cover in G prime, then